concepts or ever taken course? No, thanks.
Oops, my bad.
Yeah, so just raise your hand if you've never heard of race conditions, mutexes, semaphores, that sort of thing. Okay, looks like most of you have at least heard of these concepts, so that's good. I will go into it in a bit of detail, though, for the people that have never been exposed to this sort of thing. Okay, so in general, in any sort of multitasking system design, especially in operating systems, there's a trade-off between throughput and latency in system design. So if you want a system with a high throughput, you need your scheduler, your operating system, to have relatively low overhead and consume a small amount of processing time, right? So you can dedicate more time to the actual task, the applications you're trying to run in your system. But this also means that you're going to generally have a lower response time because your kernel, your operating system doesn't run as frequently, so you can't respond to events as quickly as you otherwise would have been able to. So a real-time operating system is an OS that prioritizes latency over throughput. So we spend a lot of time, relatively speaking, in the scheduler and the operating system, checking for events, checking the passage of time. And doing that, we can very quickly respond to events and get a very precise resolution and time measurement in the system. So what's really important about this is that you can guarantee, as application designers, we can guarantee the execution time of our task in response to an event. Right? So in a general purpose operating system like Windows, it really doesn't make any guarantees as to when an event will actually be processed. You know it will in some time, in some amount of time, but if you click your mouse, it might take 5, 10, 20 milliseconds or 30 seconds to respond if the system is busy. And generally in safety critical real-time embedded systems, we can't tolerate that sort of non-determinism. So any real-time applications built on an RTOS, generally you can think of it as a collection of tasks that each perform some independent function within the system. And tasks in a real-time operating system, generally, like broadly speaking, you can categorize them into hard real-time tasks and soft real-time tasks. This isn't really a binary categorization, it's more of a continuum, but it's useful when thinking about relative priority assignments in your system. So the most useful definition I've seen for hard real-time is a task who, if its deadline is missed, would make the system useless, essentially, right? So if you think of an autonomous vehicle, you probably wouldn't want to drive in a self-driving car that occasionally was late to apply the brakes. And you wouldn't want to use a pacemaker that had a built-in arrhythmia or something like that, right? So that's an example of a hard real-time system. Soft real-time, something we're all familiar with, is like Netflix, right? There are real-time requirements because we need to ensure that the video is displayed at 60 frames per second or whatever it might be. But if there's a bit of lag, we're used to that, it's not a big deal. So FreeRTOS is a real-time operating system that is ideal for small resource-constrained embedded systems. There are like more bulky, beefier real-time operating systems like RT Linux, which is just Linux with a patch in the kernel to enable preemption and real-time scheduling. So this would be used in things like 5G critical infrastructure for software-defined networking switches and things like that, right? Something where you need real-time guarantees, but you also need a lot of processing. We're more interested in very small resource-constrained microcontroller-based systems, and that is where FreeRTOS is ideal. So it's really just the core of it is the scheduler, which is responsible for controlling the allocation of CPU resources amongst the tasks in your system. So it provides APIs for task management, notification between tasks, queues, and mutexes and semaphores, and software timers. So a brief word on the directory structure. I don't know if we actually use this code structure in Aliasat, but if you browse FreeRTOS on GitHub, it'll look something like this. So you have all of the common functionality, the scheduler, the data structures required by the scheduler to manage tasks, semaphores, mutexes, all that. All the generic functionality is implemented in task, list, and queue.c, which are just the core files of FreeRTOS. Any hardware-specific functionality is implemented in the port layer, which is usually in a path shown here, right? It's defined for a given compiler and a given processor. So when you want to port FreeRTOS to a new architecture, you only need to implement the port layer APIs, which makes it very convenient. You know, say in a year or 2 years from now, UBC Orbit's working on the next iteration of Aliasat or whatever it might be. Any code that we write that runs in FreeRTOS will be able to run in this new system as long as it uses FreeRTOS. And all we need to do is re-implement the port layer APIs. Oh, we have a question. Oh. Makes sense. Okay, thanks, Noah. So does anybody have any questions up to here? All straightforward so far, I think. Okay. So a brief word on naming conventions, just because I'm going to show some APIs in the slides here, so you guys aren't confused. Variables and functions are prefixed with their type and their return type. You have C for char, S for short, so on and so forth. They're also prefixed with the module in which they are implemented. So task priority set is implemented in task.c, timer get name is in timers.c. All uses camel case, and macros are written in uppercase with a lowercase prefix again. So by default, FreeRTOS uses dynamic memory allocation for all APIs. So anytime the kernel requires some internal storage for kernel objects, it will use malloc to allocate that memory. They do provide static APIs denoted by the suffix static. So if you want to create a queue with dynamic memory, use queueCreate, static memory, queueCreate static. So in the OBC firmware, we will be using the static version of all APIs. Dynamic memory is generally forbidden and not preferred in real-time systems for a number of reasons. Task management. Okay. So in FreeRTOS, a task is defined by its C function that you pass to the scheduler when you create the task. Your function has to abide by the signature defined for a FreeRTOS task, which is returns void and takes a void parameter. You generally won't use the parameter passed to a function, but it can be useful if, say, you want to instantiate one task multiple times. Like if you have a task that runs an SPI driver and you have multiple SPI controllers, you can instantiate that task multiple times and just pass in the base address to whichever controller that task will use. So most task functions you'll implement as an infinite loop that is triggered by some external software event or at a periodic time interval. Right? So it should never return or execute past the end of its processing loop. If you do need to kill your task for whatever reason, you have to call the appropriate kernel APIs so that the memory can be cleaned up and the scheduler knows it doesn't need to track that task anymore. In most cases, you won't use that, though. You'll have your tasks implemented as an infinite loop. Okay, so when you create your task, you give it an initial priority in the range of 0 to whatever the maximum priority of the system is. You can change it at runtime using the kernel APIs, and the scheduler will ensure that the running task is always the highest priority out of all of the available tasks in the system. If there are no tasks to run, then the idle task will execute, which always has priority 0. So the idle task is usually responsible for things like putting the processor into low power mode. You can use it for background tasks that don't have any real-time requirements, like gathering runtime statistics and things like that. The kernel does provide a hook function, so you can add some functionality to the idle task if you need to do that. So any questions up to this point? How's the pace, by the way? We're a little short on time, so I'm going a little bit fast. But if I need to slow down, just let me know. This is fairly important stuff.
Yeah. So if you want to profile like how fast it's going, you would use those hooks on the priority 0 like idle task, right?
Yeah, that's right. Okay. And you can track how much time is being spent in the idle task, right? How many spare cycles you have in your system.
Oh, interesting. Okay, that's something we're gonna definitely have to do.
Okay, so inside the scheduler, the tasks are modeled as a state machine with 4 states: running, ready, blocked, and suspended. So when your application starts, right, you create your tasks and then you start the scheduler. All of your tasks will by default be in the ready state. So the scheduler will look at the queue of the ready tasks and move the highest priority task into the running state. Once that task completes its processing, it will either block or suspend itself. And then the scheduler will go back, find the next highest priority task, move that one to the running state. So generally, the blocked state is for a task that waits for an event with a timeout or waits for some fixed time interval. Sorry about that. Where the suspended state is to delay a task indefinitely. So if you want to wait for some event, you don't specify a timeout, it'll move the task into the suspended state, which means that the scheduler won't check that task when it goes to see if any tasks have been unblocked. So it is a minor optimization since it does slightly speed up the execution of the scheduler, but it's generally better practice to use timeouts whenever you can. So yeah, we've talked about what happens when a task runs, completes its processing, blocks itself. But what can also happen is while a task is running, a new higher priority task could become unblocked. So at that point, the scheduler will perform what's called a context switch. It will move the running task into the ready state and swap in the newly unblocked task, which would become the new running task. So that's called preemption. It's a fairly important concept in real-time systems. Okay. So at this point, you might be wondering, my task is running, right? It gets preempted. It's switched out for a new higher priority task. What exactly triggers the scheduler, right? What causes the kernel to perform that action of switching the context to a new task? And in general, the scheduler can be invoked in 2 ways. One is when your task completes its normal processing cycle, it delays itself, blocks itself, suspends itself. It voluntarily cedes control of the processor and moves itself into a not running state. And then the scheduler would invoke the next ready task. Or the scheduler can be invoked or is invoked at a fixed time interval by what's called the tick interrupt. And the frequency of that interrupt is application specific, defined in the macro config tick rate, which is in one of the FreeRTOS headers, I believe. Most common tick rates I've seen are 1 millisecond. Sometimes 10 milliseconds is also used. So that essentially means that the scheduler, a timer interrupt is firing. Oh, sorry, I have a question. Yeah, so task suspend and task resume, I believe, are called in the kernel when you block with the port max delay specified as your timeout. So if you don't specify a timeout, the scheduler will just suspend the task because it knows it doesn't ever need to check the time of that task. But you can also call task suspend manually if you know that your task will wait indefinitely for some asynchronous event. And I believe you can resume another task. I would need to double check the APIs though. I'm not certain of that. You need to be able to access its task handle, I believe.
I thought I remembered seeing that some of our tasks were suspending themselves. Maybe I'm remembering that wrong. That's why I was curious if that was something that we'd use to manage tasks, or if, like you said, it's something used by the kernel.
It can be either way.
Mm-hmm.
Like task suspend is like generally you should specify a delay if you have some idea of when your task will become unblocked. And the reason for that is that if you know that your task will become unblocked within, I don't know, 10 minutes, and you don't specify a delay, you just suspend, and then it misses that deadline, it can be very hard to debug and find out why that didn't happen, or even if that didn't happen, right? Whereas if you specify a timeout, then you can abort the system, print an error message, and find the exact point of failure.
Okay, yeah, awesome, thanks.
So yeah, the tick rate would essentially determine the time resolution of the system. So you can only specify a blocking time in multiples of the tick rate, right? So if your tick rate is 10 milliseconds and you try to delay for 15 milliseconds, you're going to be off by, you're going to either overshoot or undershoot your deadline by 5 seconds. So it's just something to keep in mind. Okay, I think that's it for, yeah. Any other questions on task management before I move on? No, okay. So we talked about it a bit, but preemption in multitasking systems can often lead to some pretty hard to resolve bugs and even hard to identify bugs sometimes, relating to data inconsistency and race conditions and things like that, if you don't properly manage shared resources between tasks. So a common example of a race condition that you'll see in any systems programming course is like a bank ATM, right? So say you are trying to withdraw $10 from your account. Your employer is trying to deposit $20 into your account. You read your account balance, you have say $100. Your employer at the same time reads your account balance, sees $100. Excuse me. Your employer then pays you $20, writes your account balance back. Your balance is now $120, but you weren't aware of that update, right? You're in the middle of withdrawing money. You weren't aware that that money was added to your account. You still think your balance is $100. So you withdraw $10, you have $90, you write that back, your balance is now $90. So you've missed that $20 payment from your employer. And then the way to manage that is by a technique called mutual exclusion, which means that you take some region of code and you ensure that it can only be executed by one task at a given time. So the way that you can handle that in FreeRTOS is by using critical sections, mutexes, or semaphores. So a critical section is a pretty basic and lightweight form of mutual exclusion that works by just disabling all interrupts. So if you remember from the previous section, context switches, or preemptive context switches rather, can only be triggered from within an interrupt, right? From the timer interrupt or from the interrupt of some other hardware event. So if you disable interrupts, then you can guarantee that for the time that you're executing the code within the critical section, no other task will be able to access that region, as long as you're in a single processor system. If you have multiple CPUs, it gets a little bit hairy. But yeah, generally you don't want to use critical sections, you should avoid them as much as possible, because they suppress all interrupts. So you can affect task deadlines, right? Because the scheduler can never be invoked as long as you have the interrupts disabled. So this example here, do you guys think this is a good use of a critical section or a bad use? What do you guys think? Hands up if you think it's a good use of critical section. Okay, no
Depends
hands.
what you're printing.
Yeah, that's true. Depends what printf does.
Yeah.
But yeah, this is probably a bad use of a critical section, right? Because it's only 2 lines of code, but printf is probably doing a lot of things under the hood, and you really don't want to suppress your interrupts for that whole time. Okay, so another way to implement mutual exclusion is by a synchronization primitive called a mutex, which mutex mutual exclusion, right? So a mutex is essentially a lock. So you would guard some critical region of code by a mutex. Any task that wants to access that code would acquire the mutex. And then if another task comes along and tries to acquire the mutex, it has to wait until the previous task completes its processing. So in FreeRTOS, they implement a mutex as a special case of a semaphore, which personally I don't really like. But yeah, so the mutex APIs are the same as the semaphore APIs, essentially. So unlike critical sections, mutexes don't prevent interrupts in the whole system, right? You can still trigger context switches to other tasks. You would only block tasks that are trying to access the same region of code that your task is working in. So they're generally better than critical sections. You should only use a critical section if you absolutely need to. So one thing to be aware of though, if you're using in any multitasking system, really, if you're using mutexes, is deadlock, which is essentially a case where you have one task waiting on, say, task A waiting on task B is waiting on task A. Neither of them will ever become unblocked and your system hangs indefinitely. So an example of that here, you have task A that takes mutex X, task B then preempts task A and acquires mutex Y and then blocks on mutex X, which is held by task A. So this would trigger something called priority inversion. You might notice here that task B is higher priority than task A, right? Because it preempted task A. But then when it tries to acquire mutex X, it's now blocked on task A. So essentially now B has a lower priority than A because it needs to wait until A is finished with the mutex until it can proceed. So the way this is handled is by a technique called priority inheritance. So when B tries to take this mutex, it would then pass its priority on to task A. So A would have its priority elevated until it finishes with the mutex, and then task B can resume. But task B tries to block on Y, which is already held by B. So now your system is stuck, you're in deadlock. So you manage this generally by, you need to always ensure that you acquire mutexes in the same order in every task that uses the same mutexes. So in this case, you could have fixed this by acquiring X and then Y in B, right, instead of the opposite order. And again, going back to what I said before, you should always use timeouts when waiting on mutexes, because that way you can catch deadlocks at design and test time, rather than finding out after you've deployed the system. Okay, so going back to semaphores, a semaphore is similar to a mutex. One common analogy you'll see that I don't love is a mutex or a semaphore is like a mutex with an associated count. So you can lock the semaphore multiple times and unlock it multiple times. So this is useful in situations where, say, you have a task that's receiving packets on some communication interface. So when it places a packet onto some queue, it might increment, it might give the semaphore, so it increments the count. And some other task might pull the packets off the queue and would take the semaphore. So as long as the count is above 0, then the tasks that try to access that queue won't block until there's nothing left in the queue, right? So a semaphore is generally better suited as a signaling mechanism rather than for mutual exclusion, right? So one subtle difference is that semaphores can be locked and unlocked from different tasks, right? You don't have to, it doesn't have to be unlocked by the same task that locks it. And another key difference, specifically in FreeRTOS, is that a semaphore has no way of handling priority inversion. It doesn't have a priority inheritance mechanism. So if you were to use a semaphore like a mutex, you could encounter this situation, but there would be no priority inheritance mechanism to solve it. So the deadline of task B would be very severely impacted. So yeah, this stuff, it's probably a bit of an information overload here, but the main takeaways are a semaphore is a signal, right? You use it to synchronize tasks or interrupts, and a mutex is for mutual exclusion. You use it as a lock to guard some region of code. So any questions up to this point? No. Okay, moving on then. Interrupts. So I mentioned this briefly earlier, but FreeRTOS provides interrupt-safe versions of most of its APIs so that you can use these mutex and semaphore APIs to enforce mutual exclusion between tasks and interrupts and to provide synchronization. One thing you have to remember, though, is you cannot use the generic FreeRTOS APIs inside an interrupt. And the reason for that is that interrupts cannot block, right? They can't wait until a mutex becomes available. You have to use the special from ISR versions. The difference in those APIs is that they won't block. So if the mutex isn't available, it'll just return an error. And then you have to decide how that should be handled. So most of these APIs will return this higher priority task woken parameter. And this tells you as the programmer that your invocation of the API triggered a higher priority task to become awoken. So what that means is that inside your interrupt, after you say signal the semaphore, if the higher priority task woken flag is true, it means that a higher priority task was woken up, and you need to invoke the scheduler so that your interrupt would not resume to the previous task that was running, but would instead perform a context switch and move to the higher priority task. So here's a little diagram showing how that works. Task 1 here is your low priority task, which gets interrupted, right, by the ISR. The ISR does something, it might read from a hardware driver and then signal, say a semaphore, that wakes up task 2. So then you would yield inside the ISR and it would resume processing task 2 instead of resuming task 1. So this can be used to make your interrupt routines very short, right? You can, inside the interrupt, you can do just whatever is required, clearing interrupt flags, reading out data from the hardware registers, and then any longer processing you can defer to another task. And it will look as though that were all executed contiguously with some slight overhead for the context switches between the interrupt and the task context. So here's just a short code example of how that works. Handler task on the left here is waiting on this binary semaphore before printing a string, right? So your interrupt handler would signal the semaphore. This flag would be set to true, and then you yield from the interrupt, and it would return to handler task once it's completed. So this sort of this is I don't know. You'll see this a lot, I guess, if you're writing driver code. Anything that interacts with hardware, this sort of design pattern will show up a lot. Okay, event groups. How are we doing for time here, Noah?
Yeah, so what I'm thinking, we can do the event groups, and then we'll have about 20 minutes to take a look at the lab. And then I'll call everyone back at 5 and just give a couple concluding notes. And then if people want to continue working on either of the labs, I'm good to stick around till 5:30. And so if anyone wants to stay and work on the labs, I'll be around to help out if they do. But if you have to go at 5, then that's fine as well.
Okay. Okay, so before I move on, then, does anybody have any questions about resource management, interrupt handling?
The port yield from ISR function that you had in like a previous slide, would that just automatically go to the highest priority task, or would you have to specify what task you want to go to?
Sorry, which function are you referring to? Is it the give from ISR one here?
The yield from ISR, port yield from ISR.
Oh yeah, so that call essentially just invokes the scheduler. So if you give the semaphore and the task that gets woken up is not higher priority than the one that's running, then port yield from ISR will do nothing, right? It will just resume with the task that was previously running. If the semaphore did wake up a higher priority task, then the scheduler would know that, right? It would be in the ready queue. It can see what the highest priority task is. So you just need to invoke the scheduler to actually perform the context switch.
Oh, okay, I see.
The only reason you need to do this is because, remember I mentioned before that the scheduler can be invoked either when a task changes state voluntarily or through the tick interrupt, right? So in this case, if we don't invoke the scheduler by yielding here, then the context switch wouldn't occur until the next tick interrupt. So if the tick rate is 1 millisecond, then worst case scenario, it might take an extra millisecond for this task to actually preempt the running task. In systems where you have a fairly high frequency tick rate, it's not that important, but like you should just do this everywhere that you use the ISR APIs. Okay, event groups. So I won't spend too much time on this, but they are a little bit confusing, and I think that they are used in the OBC firmware. So we'll talk about them a little bit. Okay. Julian, were you going to say something?
Oh, I was going to say that they're used everywhere.
Okay, good. Good to know. So an event group is a feature provided by FreeRTOS that allows you to broadcast one or multiple signals to many tasks simultaneously. And you can do this more efficiently than if you were to duplicate a bunch of semaphores, right, to synchronize all these tasks at the same time. So an event group is basically just a collection of bits, right? It's like a big bit mask where each bit value in that mask has some user-defined meaning. So FreeRTOS does not dictate what the bits in an event group actually signify, right? You as the programmer have to provide meaning. So yeah, you can see this is what an event group would look like, right? You'd have bit 0 would correspond to some flag, bit 1, 2, 3, 4, 23, whatever. So you can block a task to wait on one event or on a combination of events to occur. And you can also do that from multiple tasks at the same time. So yeah, here's a little short code example to show you how this works. So you define these masks that signify what the bits in the event group actually mean. You have this task that delays a little bit and sets the event group bits rather. And then you have a task that blocks and waits for these events to occur. So I don't have the actual prototype here, but so this function call here would wait for one of the first task, second task, or ISR bit conditions, right? Because this parameter here is false. So you're waiting for only one of the events to occur, not all of them. If you set that to true, then all 3 of these bits would need to be set before the task becomes unblocked. So in this case, you don't know which bit is set. You need to check the event group and see what event occurred. So they're pretty convenient. Event groups can be used from interrupts, but there's some minor caveats that you should be aware of. For one, the event group, the actual events, if you set a bit from the ISR, the events aren't generated directly within the ISR. And the reason for that is that FreeRTOS doesn't allow non-deterministic operations to be performed inside interrupt context. So when you set a bit, you could unblock multiple tasks simultaneously, and the scheduler doesn't know ahead of time which tasks will be unblocked. So it doesn't allow the bits to be set directly in the ISR. Instead, it defers the action to the daemon task in the RTOS, which is just some internal task that can be used to run asynchronous processing that you don't want to do inside an interrupt. So you need to be aware here if you're using an event group to signal a high priority task, right? Because that task still needs to wait until the daemon task has an opportunity to run and generate the bit event. So this previous example here, right? We went directly from the ISR into task 2 after we generated some event inside the interrupt service routine. In the event group case, we would need to have this intermediate step where the RTOS daemon task would have to run. So if you have some intermediate level priority tasks that are higher priority than the daemon task, but lower priority than the task that would become unblocked by your event group, your higher priority task would need to wait until all these intermediate tasks have opportunity to run and until the daemon task is run. So it's just something to keep in mind if you're using event groups to synchronize very high priority tasks. Yeah, no, good question. Off the top of my head, I don't know what the default priority of the daemon task is. I'm sure, I think it is higher priority than the idle task, but off the top of my head, I don't know.
Okay, cool.
And it can be reconfigured for your application depending on what the application needs are too, right? It's not fixed by any means. Okay, so that's all I have. So we can move on to the FreeRTOS demo. Let me get the slides open here. Sorry, before I start the demo, does anybody else have any other questions about any of the sections we covered? No? Okay, good.